With the Playground feature, you can explore protein sequences with AI models trained on billions of amino acids in minutes. We use transformers, state-of-the-art machine learning models that are trained on most of the protein sequences found in nature, both those we have assessed experimentally and those that still have to be studied. They can help uncover promising new insights from amino acid sequences. Let's see how it works. The Playground can be accessed by selecting the appropriate tab on the upper right corner of the screen. The Playground allows you to explore either custom new sequences or ones from the polypeptides present in your active design. Let's first look at one of the defensin chains in the uploaded structure. As we can see, the model returns an estimated distribution of amino acid probabilities at each position. However, the colors, or probabilities, are not particularly well defined, as the sequence is rather short and could go anyway. We do see though that the cysteines, which are essential for the stability of the protein, have a visibly higher probability than other residues. To see more biologically meaningful results, we need to check out the full sequence of the gene product before it gets modified in the organism. Here I have retrieved the full sequence of human defensin from UniProt, so let's apply the model to it. And then we hit the Submit New Sequence button. Now, the probability landscape is much cleaner. We can see that there is a strong signal from the N-terminal methionine. Then, in the beginning, we see that the model wants to put a string of leucines, hydrophobic, helix-forming residues there. This is the signal peptide, which dictates where the protein will go. It should be indeed hydrophobic and helix-forming. Interestingly, at position 2, we see a strong preference for arginine or lysine, both positively charged residues. Due to positive inside rule, these are obligatory at the beginning of a signal peptide. Following the signal peptide, we see a propeptide sequence, which has no functional constraints and as such seems to have mostly stereochemical ones, such as proline in position 21. We see that the propeptide sequence is strongly biased towards negatively charged amino acids, aspartic acid and glutamic acid. These are here to stabilize positively charged mature defensin when it assembles. Notably, we see that cysteines, important for stability of the cleaved defensin, still remain highly favorable. For each position in the sequence, we have the presence probability of each of the 20 natural amino acids displayed as a heat map. It can also be visualized as a bar plot. Another way to leverage the power of these language models is with our sequence generation tool. By selecting one or more positions in the sequence as mutable, we can then generate most probable variants. This slider here allows me to adjust the number of generated sequences. That's it. We've seen how to get insights on protein sequences using state-of-the-art machine learning models in DeepChain's Playground. Thank you for watching and enjoy DeepChain.